Good day and welcome back to part one of our discussion on limit laws. In the previous sections, we have defined what we mean when we say the limit of a function is equal to L. We've explored how we could maybe evaluate these limits both graphically and numerically by making tables, but at the same time we finished our previous video by indicating that there are limitations to that approach and we'll need a more systematic approach. And that more systematic approach comes from the limit laws, which we are going to introduce and spend significant time with in this section. I also want to throw out there before jumping in that starting our Calculus 1 experience with limits may seem like kind of a strange or weird starting point. But I'll note it plays a fundamentally important role in the course. The two main topics that we will discuss are differentiation and integration. And in order to define a derivative for an integral, we have to go back to using limits. So spending the time now to build up kind of that strong fundamental or foundational understanding of limits is going to pay dividends down the road. So with that in mind, let me remind you what we talked about previously. We said, at least intuitively, the limit as x approaches a of a function f of x equals L means if we have a value of x close to a, f of x is going to be close to L, with a few small caveats. But intuitively we're saying for x close to a, and maybe I'll just throw those in here, close to a, and this is on either side of a, but not equal to a. Remember, when you're calculating limits, it does not matter what happens at that value of a. So for x close to a, f of x is close to L. And then we also saw that this idea of what happens on either side led us into one-sided limits, which gives us a very useful way of sometimes showing a limit may not exist. So let me remind you of that property. We said that the limit as x approaches a of a function f of x equals L, this is true if and only if, i.e. equivalent to, saying that the limit as x approaches a from the left of the function is equal to L, and the limit as x approaches a from the right of the function is also equal to L. And I will say it in words, but I'm not going to write it down. Note if the one-side limits do not agree with each other, the limit of the function does not exist. Before jumping into our limit laws, which really is the main topic of discussion, I want to look at an example we could have done at the end of the previous section. In this case, we have a limit as x approaches 1 of the what we might call a rational function, the polynomial x minus 2, divided by the polynomial x minus 1 squared. So just a reminder, because it will come up later on in this section, a rational function is something that is of the form a polynomial over a polynomial. And I do want to note that this rational function is undefined at x equals 1, which is perfectly fine because remember when we are evaluating the limit, it does not matter what happens at 1. It only matters what happens for values close to 1. And because it's a rational function undefined at 1 because of the domain of the function, we can't divide by 0, there's going to be a vertical asymptote at x equals 1. And when you are in pre-calculus, you spend significant time kind of discussing, how you would graph this rational function. But I'll just very quickly note that it has an x-intercept at 2. And then if you check a couple values close to 1 on either side, and note that the x-intercept would be minus 2, roughly speaking, the graph of this function is going to look something roughly like this. But even this rough graph that, once again, we could certainly use our calculator to help us out here, but I'll note when it comes time for exams, we won't have that calculator. But once we have this graph, we think if we have values of x close to 1 on either side, what are those outputs going to be close to? So whether it's on the left or on the right, we see that as we get closer and closer to 1, those outputs are getting indefinitely larger and negative. So the observation that we want to make from this is that the limit as x approaches 1 of this rational function x minus 2 times x minus 1 quantity squared is equal to minus infinity. And note when we write this out, we're not suggesting that plus or minus infinity is a number, but it's an idea that indicates that we are getting extremely large and negative. And let me just note that the limit as x approaches a of a function can be plus or minus infinity, which is something I wanted to note at this point in passing, but it will certainly come up later on at other points in the course. So for now, what I'd like to do is kind of shift gears and get into our limit laws. We're going to think of our limit laws as almost justifying for us that we can do exactly what we want to do with limits. So to start, I'll walk us through the first 5 of these limit laws. Then we'll take a break for an example, and then we'll take a look at the remaining 5. So a total of 10. So to begin, we have kind of a small hypothesis. We're going to suppose c is a constant, wherever it comes up down here, and that the limits as x approaches a of the function f of x and the limit as x approaches a of g of x both exist. So those functions have limits. Remember, a limit does not need to exist. And I'm going to throw in one small additional statement because of our previous discussion here, that they both exist and they are finite, i.e. the limits are concrete numbers. They are not plus or minus infinity. Then if that is the case, if you have a limit of a sum of functions, you can break that up into the sum of the individual limits. Same thing with a difference. If you have a limit of f minus g, you can write that as the limit of the function f minus the limit of the function g. So once again, you can almost just do exactly what you want to do. These limit laws are telling you kind of intuitively what makes sense. If you have a constant inside a limit, that constant can always be pulled out front of the limit. And a limit can also be broken up over a product. And with all of that in mind, it's probably not surprising then that you can also take a limit and break it up over a quotient. That is, you can take the limit in the top, divide it by the limit of the bottom, but of course there's one small stipulation that we have to place. We don't want to divide by 0. So that is, as long as the limit of the function in the denominator, or the bottom here, is not 0. So let's go ahead and pause for a quick example, something a bit more graphical. In blue, I've sketched the graph of a function we'll call f of x. In red, we've graphed the function g of x. And I have several questions based upon the graphs of these functions. By inspection of the graphs, you should be able to easily determine what is the limit as x approaches 1 of f or g. Let's go ahead and pause the video. I would like you to take, 2-3 minutes, whatever's necessary, and determine what the values of these limits are. Okay, so I'm going to assume that you've paused the video, you've thought about these for a few minutes. If you haven't paused the video, certainly make sure to do so now and figure out these two limits. And as I'll keep reminding you, you take out of this what you put into it. So taking the time to think about it on your own before coming back to how we complete the problems together is extremely beneficial for the learning process. So I'm going to go ahead and apply the limit laws. So the first limit law that we can apply is number 1. That tells us we can break this up into the limit of the first function. So we have f of x plus a second function, 7 times g of x. And then I'm going to go ahead and take it one step further. And then we'll evaluate the limits. I'm going to note from that third limit law, and I'll never ask you to reference a specific limit law. I'm doing so just if you want to kind of turn back to that previous page. We can pull out that constant 7. And the idea with the limit laws is to break it down into its smallest, simplest, easy to handle components. So the limit as x approaches 1 of f of x. If we look at f of x above in blue, if we have an input close to 1, we see those outputs are going to be close to 0. And for g of x, we see that for an output close to 1, those outputs of the function will be also close to 1. So the limit as x approaches 1 of f of x is equal to 0. The limit as x approaches 1 of g of x is equal to 1. And you could leave your answer exactly in that form, or we could note that this is equal to 7. And for the first of probably many times in upcoming videos, I'm going to point out that when you write up your work, it should essentially look like this. Whenever we possibly can, we line things up vertically in a column. When we're dealing with limits, we write each limit at every single step. We write the equal signs. And when you have evaluated the limit, like we've done going to this third line, we stop writing the limit. If I run out of room and I need to write more, I just kind of draw an arrow up and I start a new column working downward. That allows someone to hopefully quickly and efficiently read and follow your work. And as you will hear me say over and over again, notation is to mathematics what punctuation would be to an English course. Extremely important. Mathematics really is a language. For that second limit, we can use the property 5 at the top of this page as long as we don't end up dividing by 0. So you don't need to write anything down, but you just need to keep that in mind. So this would be the limit as x approaches 1 of f of x divided by the limit as x approaches 1 of g of x. And since we're going to complete this in just another quick step, I'm going to go ahead and just write out what this is in a horizontal line. So the limit as x approaches 1 of f of x is 0. The limit as x approaches 1 of g of x, the red function, is 1. So the value of the limit itself is 0. And note, as long as you do not end up dividing by 0, you are okay to use this limit law. If it was g of x over f of x, then we would need to go back and find another approach to evaluate the limit. And this finishes the discussion for part 1. We will pick up at the beginning of part 2 with the remaining limit laws and then spend quite a bit of time investigating examples. So stay tuned and take care.